Hi, so this is my electrodynamics term project on the conservation of momentum in electromagnetic fields. So to start, we want an impetus. We know that there's a problem with Newton's third law in electrodynamics. This is because when we analyze a system like this one, we see that the forces are not always opposite directions. In this, we know that the particles aren't necessarily steady currents, so we can't really use the normal force equations that we have. But we know that their directions are consistent with what we see in electrostatics. So, for example, like the B field here at V2 is going to be into the page, which gives a force to the right, and then this one gets a force up, and these are not anti-parallel vectors. So we know that Newton's third law does not obey in this system, which is an electrodynamic system. And so that's a problem because we rely on Newton's third law to provide us with conservation of momentum. Because if we had a system of particles that that did not obey Newton's third law, then we could have random increases or decreases in momentum, which is nonsense, and we can't have that. So we need something to account for this, and we want to analyze Maxwell's equations and see what we can find for what may cause conservation of momentum to be maintained in electrodynamics. So we suspect that the fields are what allow for conservation of momentum to be maintained. So we want to get the general force equation into terms of only the field and see what we can derive from there. And so we start with this general equation integrated over a system omega, any system omega. And we see that this rho v is can be substituted as j, just generally. And this J and rho can be substituted in by Gauss's law and Maxwell's equation, or Maxwell's correction for Ampere's law. And so this would get us an equation consisting only of fields and time derivatives of fields. And so then we get that substituting those equations in gives us this equation. And this is, of course, distributed over the cross product of B. And then we can use the product rule and Faraday's law to get this in terms of this time derivative over a single term and not involved with any cross products. And this will be useful later on in the derivation. We also note that we added this term over here. This did not come from the original equation, but this term here is allows for further symmetry later on in the equation. And it's allowed to be added because we know that divergence of B is always zero via Maxwell's equations. And so, of course, 1 over mu naught divergence of B times B will also always be zero because it's obvious. Um, but yeah, this is just for further symmetry in the later equation. And so we do further side calculations to get to that further symmetry. And of course, I'm not going to exhaust this entire, like, I'm not going to say this entire equation, but this is what we used to get further. And then the same applies for B. But of course, we had to permute this cross product to get to the same uh, formulation as E had, and with just a negative sign. And so we plug this back into our force density equation, and we get this monstrosity, which is not very, we can't glean much information from this. So we need to define a new quantity. And the new quantity is the Maxwell stress tensor. This is a rank 2 tensor comprised of forces per unit area. And these are forces due to the electric and magnetic fields in some region. These forces can be pressures, which are the diagonal elements, or shears, which are the off-diagonal elements. So a pressure is just a force per unit area applied to the direction of a surface in the direction of the force. And then the shears are a force applied to a direction onto a surface that is oriented in a different direction. So for example, if we wanted the force per unit area in the y direction acting on a surface oriented in the z direction, we would have, of course, this EYZ minus, and then this term goes to zero because this is a Kronecker delta here, which is zero for not equal indices and then one for equal indices. So this term would arise only for example, XX, YY, or ZZ. But here we don't have equality, so we only get these terms here, EYZ and BYZ. And so, yeah, this is a force per unit area, and then we want to we want to plug this into the force density equation somehow. And so we do that by taking the divergence of it. And when we take the divergence, we want to use the inner product notation, the summation notation. And so this allows us to see kind of clearly how to do an inner product with a tensor here. Um, and this is what you get here. Right, so you're summing over the XYZ indices. So of course we have to remember that nabla here is the differential operator, and we can model this in this way as a three vector of the dx, dy, and dz. So then nabla x is going to be your d over dx, nabla y is going to be your d over dy, nabla z is going to be your d over dz. And then of course, since the Kronecker delta has equality, is equal to one only for equality, this term is just going to be nabla j here. Uh, and then of course the b parts are going to be the exact same, just with a 1 over mu naught. And then this can be simplified further if we distribute out the ej's for these terms, and then we distribute out ex, ey, ez for these terms. We see that this is exactly this equation here, this directional derivatives, and then divergence applied to a scalar field. And this, yeah, this is exactly what we have here. And then the same works for the b parts. Obviously, this is just have a 1 over mu naught over it. And then we notice that this is a single component of what we have in the force per unit area equation that we have back here. So, including this term, because the linearity works here. If you can distribute this nabla to both of these and then pull out the constants, and we have exactly what we have here. Of course, negative one half epsilon naught here. Um, yeah, so the full vector version of this divergence, so just divergence of t, is going to be a vector because you're taking a dot product of a tensor, so it's going to result in a vector. So yeah, so the full vector version of this divergence is going to be a vector that's equal to that term that we had in the force density equation. And so we can substitute here. And then we get this much prettier equation that we actually can glean some physical meaning out of. Right, so we have to remember that this is a force density. Or this is a force density and this is a force per unit area, the derivative of a force per unit area. And then this has to be it's a time derivative of something, but if we recall, the time derivative, a force is equal to time derivative of a momentum. So then this E cross B must represent some kind of momentum density, right? So that's what we find uh, once we substitute in as well the pointing vector, which we recall is 1 over mu naught E cross B. And if we multiply both by both constants and take the time derivative, then we clearly see that this force density becomes divergence of T minus mu naught epsilon naught d over dt of S. And so we see that this S needs to be some kind of momentum density, or this mu naught epsilon naught S needs to be some kind of momentum density just based on our units. Um, and so by divergence theorem, we get this equation here. So the total force of some system is equal to this flux through the boundary of the system of your Maxwell stress tensor minus some constants times the time derivative of the pointing vector throughout that region. Okay, so let's relate this back to momentum. So we know that according to Newton's second law, that the time derivative of the mechanical momentum of some system is F. So we can relate that back to our total F of our whole system. So we see that the time derivative of the mechanical momentum is this flux of T minus this time derivative of S over the region. And then we can get the time derivative on both sides. And so we see that d over dt of P mechanical plus mu naught epsilon naught integral over omega of s d tau is equal to the flux of T through this region. So this matches exactly the conservation equations that we've seen in the past. We had the time derivative of some quantities equals the flux of some other quantities. And just like local charge conservation, right? The time derivative of charge is equal to the flux of J. Um, and so we see that this obviously must be another conservation equation. Um, and then and then this term here must be a momentum because it's adding with a mechanical momentum. So we call this term the electromagnetic momentum. And here we have reversed the divergence theorem on this T, and then we've taken it down to densities rather than full values. And so the time derivative of the mechanical momentum density plus this value here equals the divergence of T. And so we call this value here the electromagnetic momentum density. And this is what allows for conservation of momentum to be maintained in electrodynamics. Because the fields themselves have some attributed momentum. Um, yeah, so this sends us to a much more beautiful equation that shows the conservation of momentum in electrodynamics. And that is it. And a big thing to note also is that we did not use any other models or theories other than Maxwell's equations. This equation simply dropped straight out of Maxwell's equations. So it is just like local charge conservation in that it is intrinsic to the model. And because of this, it offers a lot of confidence that Maxwell's equations are a complete model.